infinite volume.
Well, thanks a lot for the introduction and the invitation. Everything I'm going to talk about in this talk is based on joint work with Roland Bauerschmidt, who is now at the Courant Institute at NYU, and Hendrik Weber, who's in Münster. And we've been interested in a certain singular stochastic partial differential equation, which I refer to as the phi42 dynamics. And in particular, what we want to understand is what happens to it in long time when we consider it an infinite volume. And well, infinite volume is going to make a difference. So we're interested in its invariant measures. So what is this dynamics about? Well, let me say that you're very welcome to interrupt me at any point in this talk. And so the dynamics I want to talk about is the one you see on top of the slide, where the unknown phi is a function of time and space. So it's an infinite dimensional equation where you have a Laplacian term, a phi cube term, which has a sign, which makes sure your field phi doesn't grow too much. And there's a linear term, which doesn't have a sign. And the reason why this equation is stochastic is because this psi here is a noise, and it's a white noise. So it's a very irregular forcing, which makes it so that I call this phi a function, but it's not actually a function, it's a distribution. At least depends on the dimension, but in the cases I'm going to be interested in particular in 2-dimension, it's a distribution. So it's a random distribution evolving in time and defined on the full space. Now, the question I'm going to be interested in is what can we say about this random distribution or its law in long time? Is there one invariant measure? Is there more, or are there more? And can we say anything about convergence rates in case there's only one? In order to explain to you where this question comes from, because it might seem fairly abstract, looking at this particular equation and asking a question about invariant measures, actually this the question of what the invariant measures look like, is related to the presence of phase transitions in the model. And the fact that we're in the full space means this is precisely the situation in which we're going to see these phase transitions, and this is going to play a role on uniqueness or non-uniqueness of invariant measures. So I'm going to try to explain this, providing you some intuition of what the invariant measures are expected to look like and how we can construct them. And I'll then tell you what we can prove and spend quite some time on how we prove it, which is a beautiful idea due to Holly and Struck, and then Struck and Zegelinsky, and then Zegelinsky quite a lot by himself. A beautiful idea that comes from statistical mechanics model. So it's the same equation as up there, except that instead of RD, you have ZD. And this is what I call statistical mechanics. And for this kind of objects, these people have developed a very strong and very versatile approach to proving uniqueness of invariant measures. And the proof is very simple, so I'd like to explain that as well as I can. So let me start by trying to give you an idea of what we can expect about invariant measures of this dynamics in infinite volume. I told you that this phi4 stochastic partial differential equation is an infinite dimensional equation because my phi, it has, if you want, there's a different value for each point of space. But let's assume for a second that it's finite dimensional. In this case, it's tempting to see this drift term as some kind of, as the gradient of a suitable energy functional, which I write dH. And this strange d here is by gradient, I mean that I think of each phi of x. So the value of the field at a given point, I think of it as an independent variable as the position is varied. And so this derivative differentiates with respect to the value at one fixed point. And if you do that, what the energy functional H or Hamiltonian should look like is a Dirichlet energy term where you're integrating this gradient square on the full space. Then there should be a phi to the 4 term which is where the model gets its name from, why it's called the phi42 dynamics and not the phi32 dynamics. There's a quadratic term, yeah. Now, as you may know, if you look at a Langevin dynamics in infinite dimension, so something that looks like this with a drift given in terms of the gradient of some energy that I call U, then under very mild conditions on what this U is, you expect that this equation is going to have just one invariant measure, which is going to be given as a negative exponential of your energy functional. This tells us at this very heuristic level that if we want to understand invariant measures of this stochastic partial differential equation, this phi4d at this moment, I'm not restricting to dimension 2, so this phi4d dynamics, it's a good idea to try to understand measures that look like a negative exponential of this energy that I wrote here. Now, the thing is, this is not so easy to do. It's actually quite problematic because of two different problems that I call a small distance problem, or ultraviolet, if I think in terms of frequencies instead of distances, and a large distance, or infrared problem. What do I mean by that? Well, let's look at the small distance problem first. Remember that in my equation, I had this very rough white noise term, which means I expected my solutions to be distributions rather than functions. Now, defining the square of a distribution is not that big a deal because we understand Gaussian objects very well. Defining a fourth power of a distribution, however, is quite complicated to do because this thing is not actually defined pointwise, this phi of x. So taking the fourth power, I don't know how to do that in general. Well, one has to explain how we do it in every single case. This is what I call my small distance problem because it's really related to the fact that the field phi I want to evaluate this energy at are irregular. They're not functions, they're distributions. I have another problem, however, which is related to the fact that I'm trying to integrate this quantity on an unbounded domain, on the whole of Rd instead of on some finite box. So what's that problem about? Well, if you look at the equation, the noise that, well, actually I can show it to you. The equation was what you see on top here, and there's no space dependence anywhere. It looks the same at every point in space, even with respect to the noise, psi, which you can imagine as one independent standard Gaussian random variable at each point in space. So really this phi, there's no reason why it should have any kind of decay in space. And I expect it to be order 1 everywhere in space, which means that if I'm integrating something of order 1 the full space, I always get something infinite. This is what I call the large distance problem. Now, what I'm going to try to explain you is how we can solve these, how people have solved this. This is by no means what we've been doing with Hendrik and Roland. This has been known for a while. And the way people proceed is by introducing suitable regularizations. 2 regularization parameters, 1 small distance regularization and 1 large distance regularization. There's several ways to do it, but the one I want to consider is a so-called lattice regularization, where I solve my large distance problem by introducing, well, instead of considering my field on the full space, I just cut it off after distance L, so I consider things on the torus of side length L. But at this point, it's still a continuum torus, so I still have the problem that my field is an infinite dimensional object that's a distribution. So to avoid this regularity, this small distance problem, I introduce an additional parameter, which is this mesh epsilon. In this case, I want to write, so once I've done that, I want to write the measure I'm after, which is this negative exponential of my energy term, d phi. I want to approximate it or build it by getting rid of this regularization, starting from this measure that you see here, where this HL epsilon is something I'm going to define in a second. But now the field is not a distribution, is not infinite dimensional anymore. is just a big vector associating with each node of this lattice a real value. Okay, so let's start from this and let's see what the energy should look like in order to get something meaningful. Because what I'm interested in is not this object on the lattice. I'm interested in what happens on the full space. So let's start by seeing what this energy looks like and what happens when I remove the small distance regularization.
Sorry, Benoit, if you'll allow me a quick question.
Yeah.
Do you have an intuitive argument or counterexample of a notion of why your large distance problem would not be solved by just taking the finite volume stationary state and just repeating it? Because your white noise is translation invariant, right?
Yes. And indeed,
is it what actually happens?
Well, so it's in infinite volume. See, yes, the invariant measures I'm going to be interested in are translation invariant. But
But do they have
okay,
like
so if
infinite volume correlation or something like that?
Sorry?
The correlation, do they decay fast or are they long range?
It depends. It depends on the temperature.
Okay.
Sorry, it depends on this parameter mu. So at high temperature, which means large mu, things are going to behave like, well, small distance correlation. So things are basically local. At large values, at very negative values of mu, which means low temperature in this model, then you get large correlations. This is what I'm going to mention the next slide, actually. But yeah, so you cannot just copy paste the same, take the torus of psi length 1 and iterate it, because then you're actually introducing correlations.
Yeah, okay, that makes sense. Okay, thanks.
So, Benoit, maybe I can ask a question related to Clément. So the measures that you're going to construct are, in some sense, Gibbs measures?
Yes and no. I'm only going to, okay, so the infinite volume ones are Gibbs measures, and they're the only one. But I don't want to talk about that because I don't want to talk about boundary conditions in this rough distribution setting.
Okay.
But essentially, yes.
Okay.
And I'm going to prove that there's only one way to take the limit as L goes to infinity anyway, at least in a suitable regime. So there's only one Gibbs measures. Except nobody has proven it, but that's the idea.
Okay, thank you.
All right, so yeah, the energy I want to put in my regularized measure looks like this. So now I'm in finite volume. I'm in finite dimension. My field is just a big vector, which means my continuous integrals are turned into Riemann sums. So this epsilon d is a Riemann sum parameter, and as epsilon goes to 0, you imagine this going to an integral on the torus of psi length L. The gradient, perhaps I can show it to you again, the gradient square in the phi4 and the phi square are just reproduced in this regularized setting, which means there's a Laplacian term, but discrete Laplacian, regularized at scale epsilon. So this object, if epsilon goes to 0 and phi is an actual function, converges to the actual Laplacian phi. And the phi4 term, which is unchanged, and a phi square term, which comes with this term in red that is called a counter term, and that I'll discuss in a minute. What people have managed to prove, and this was quite a big deal back in the days, was that if one chooses this counter term in a suitable way, then it is possible to remove the small distance regularization parameter epsilon, in the sense that you get a well-defined limit for your sequence of measures, or for your family of measures, as epsilon goes to 0. And by meaningful limit, I don't know if that's what I said, but that's what I wanted to say. I mean, you get something that looks like phi4, that looks like this question, this measure below, in the sense, for instance, that it satisfies the correct integration by parts formula. So you get the right object, but in order to do that, as I mentioned, well, you can only do it by looking at a measure on distributions and not on functions. So there's no way you're going to get a limiting measure that's non-trivial, looks like phi4, if it's not on distributions. This is where this counterterm comes into the picture. Because if you look at your regularized approximation, then your field is just a big vector. It's no problem taking the fourth power of the field is just a number at each site. So this means that as epsilon goes to 0, this phi to the 4 thing, because it's supposed to converge, because phi is supposed to converge to a distribution which doesn't have a well-defined fourth power, this thing has to blow up. And people know how it blows up. It actually blows up in a different way depending on the dimension, but precisely at the speed that is compensated by this counterterm. So this is why the counterterm is introduced. It's not to make things worse on purpose. It's because phi to the 4 doesn't have a limit, but phi to the 4 plus counterterm phi square plus another counterterm that's independent of the field, so I'm not writing it, this object has a limit. And you might have noticed that I'm defining this counterterm in dimension 2 and 3, and not others. Well, there's actually a deep reason for that. In dimension 1, it turns out that there's no need for a counterterm. The phi under considerations are actually functions. So things are very well, or at least much better understood in that setting. On the opposite side, in dimension 4 and higher, it is a very difficult result, but now known, that there is no way to choose a counterterm in such a way that you get something that looks like phi4 in the limit. So somehow the only two relevant dimensions are dimension 2 and 3. Okay, so at this point, what I've told you is that you can introduce this regularization with two parameters, small distance and large distance. And if you're ready to work quite a bit and introduce this counterterm, you can define a meaningful notion of this phi to the 4 measure in finite volume. All right, so let me now explain to you what happens when we remove the other parameter so that we get something in infinite volume, which we hope would be this exponential minus energy measure that we're after. See that at this moment, this new L measure looks exactly like what we would want, except that the integrals are only on the finite region instead of on the full space. Now, removing the parameter L is a bit different, is actually qualitatively quite different, because this is the limit in which you see the physics, in a sense. This is the limit in which you see large size effect, in which you see phase transitions. And precisely, this Ising model has a phase transition. So what do I mean by that? Let me start by telling you that the way you should think about this phi4 model, if you're not happy with having to think about distributions, just think of it as a very fancy Ising model. It's a complicated analog of the Ising model, just plus or minus spins, and it has exactly the same large size behavior. What I mean by this is that there is something that plays the role of a temperature parameter in this model, meaning if you fix the lambda, which is the strength of the phi to the 4 term, and you vary the parameter mu, then when mu is larger than some threshold value, mu critical of lambda, you're in a high temperature phase, which, well, you can quantify this by saying that correlations between the field at different sites are sufficiently small, these correlations being quantified in terms of this susceptibility object, which is just the variance in central limit theorem scaling of the sum of the field at each site. Same as the Ising model. Now, on the other side of this threshold, this susceptibility parameter blows up. So at what I call a low temperature phase, below this mu critical, you have strong correlations in your model. And I am not going to make any claim whatsoever regarding what it means for Gibbs measures of the phi42 field theory. People have studied that, Albiverio, Högner, and Zegolinsky, for instance, at some point. And also, Glim, Jaffin, Spencer, Fröhlich, Simon, Spencer, they did look at boundary conditions, but I don't want to do that because it's complicated. So, but what you should expect is that this threshold for correlations is the same as the threshold for uniqueness or non-uniqueness of Gibbs measures. This is known in the case of the Ising model. It is not known for phi4, but reasonably you could expect one could work it out. Okay, so this is all I wanted to say about what invariant measures of the dynamics may look like. So let me summarize before I go on to tell you a little bit about the dynamics. I've interpreted this phi4 dynamics as some kind of Langevin dynamics, which gave me as candidates measures that look like a negative exponential of some energy term. But I've told you that it's possible to rigorously build these objects in finite volume, but in infinite volume, it depends on whether or not there's a phase transition. And you shouldn't expect, if you're at low temperature, you shouldn't expect to have just one of these objects, which is a strong indication that maybe there's more than one invariant measure for your dynamics at low temperature. And actually what I'm going to prove that at high temperature, indeed, there's only one invariant measure. Now, so far, everything I've told you about the dynamics is very hand-waving. I haven't actually told you why or how to make sense of what it means to solve, to be a solution of this dynamics. Haven't told you anything about well-posedness, so that's what I'm going to say now. And I'm also going to justify this claim I made about seeing this dynamics as the Langevin dynamics of the phi4 field theory. This is something you can actually justify in finite volume. From now on, and throughout the rest of the talk, I'm going to work in dimension 2, which turns out to be much simpler. If you think about this counter term from a few slides ago, it's much more controllable than in the 3-dimensional case. And this is the only dimension for which we have results anyway. So I'm in dimension 2. And in this case, what was shown a few years ago is that there is a solution to this equation, and only one solution, in a very strong pathwise sense. So what do I mean by that? I mean that if you place yourself in a suitable space of distributions, the so-called Bezoff space that I'm not going to define, and that you should just think of as some Sobolev space of negative order, they're closely related, then you can start your dynamics from any distribution in that set, and you're going to get a continuous trajectory that at each time takes values in this negative regularity set, and which solves this equation. Now, what do I mean by solving this equation? I mentioned it solves this equation in a pathwise sense, and more precisely, constructing a solution was something that was made possible through a very powerful idea due to D'Aprato and Debuche now more than 20 years ago, of decomposing your field into different pieces. One of them is going to be very rough and is going to be the reason why your field is a distribution in the first place. And the other one is going to be much smoother. And the two are very much dependent one on the other. It's not a decomposition in terms of two independent objects. But the nice thing is that your rough object is something you understand very well because it's going to be the solution of the stochastic heat equation. It's just a Gaussian object, an Ornstein-Uhlenbeck process. The remainder you define as the mild solution of whatever you should put so that the sum of the two solves this in a meaningful sense. So the remainder should satisfy this equation that you see here, in which you see appearing powers of V, products of V with this distribution Z, with the square of this distribution, with the cube of this distribution. What I claim is that this V object is sufficiently regular so that all these products are well-defined, first of all, because it's not easy in general to define the product of a function and distribution. In this case, you can make sense of them. And this Z square and Z cube, remember that Z is a distribution, so it's not clear how to take the square and the cube of a distribution. And this column signs just indicate what we mean by this, some kind of regularized square and regularized cube called Wick product, Wick square and Wick cube. not going to get into details at this point. Just want to say this is how you build the solution by splitting it into two, solving an SPDE but linear, and then solving just a PDE because V is an actual function, a PDE with random right-hand side. All right. Now that we have a solution, let me try to make more precise what I meant by the Langevin, the phi42 dynamics being the Langevin dynamics of the phi42 field theory. This is something that we can make rigorous in finite volume. People know how to do that. I've known how to do that since a few years, for a few years. More precisely, if one considers the dynamics in finite volume, which is just the same thing as the dynamics in infinite volume, except that you make the noise periodic, for instance, if you want to define the dynamics on a finite torus. And by a periodic noise, I mean that it acts on a test function by the original noise acting on the periodized version of the test function. And this object, you can define it using the D'Aprato-Debuche approach in the same way. But now things are finite volume. So if you want, the space is compact in some sense, which means you're always going to have a unique invariant measure for this dynamics, something that people know how to do. Same as for an Ising model in finite volumes. It's just one way of defining an Ising model in finite volume. And this unique invariant measure is the one I constructed before. It's this phi42 field theory. So the one that had this exponential of the energy term truncated in finite volume. The integrals are truncated in finite volume here. So in this sense, the dynamics is indeed the Langevin dynamics for the phi42 field theory. And people even know that there is exponentially fast convergence to this unique invariant measure, but the rate at which the convergence takes place is not known. And in particular, it is not known how it depends on the volume, which is the interesting thing, because that's where you see the presence of a phase transition or not. All right, so this is all I wanted to say about the connection to the field theory, what the invariant measures may look like in the dynamics. So let me summarize before I tell you about what we can prove and how we prove it. Is there any question at this point? Okay.
So you mentioned about the boundary. You mentioned that you didn't really want to talk about boundary conditions before, right?
Yeah.
But I'm going to insist a little bit. So in this result of the convergence to the invariant measure, are these boundary conditions relevant or not? How they take the boundary conditions?
As far as I know, everything is on the torus.
Okay.
There's no boundary condition.
Okay, periodic boundary condition, yeah.
I am not sure what has been done with boundary conditions in this SPD setting, but I would say very little.
Okay.
Very little. And well, in a sense, well, you could see this whole SPD business of SPD procedure of describing invariant measures, which is more or less what we're going to do here, construct an invariant measure in infinite volume through the SPDE. You could see it as a way to completely bypass discussing boundary conditions, at least at high temperature, because there's only going to be one. So in a way, the dynamics is more local than the measure, which makes things, which allows you to ignore boundary conditions in some sense. At least that's, yeah.
Okay, thank you.
All right, so let me summarize where we stand. I've told you I have this nice Langevin dynamics heuristics level at a heuristic level, but I can make it rigorous, at least in finite volume. So at least with this, we have a, let's say, strongly encouraged to think of our infinite volume invariant measure candidates as being related to what happens in infinite volume for the field theory, and in particular with respect to its phase transition. Because these measures do have a phase transition in terms of this temperature-like parameter in front of the linear term. And in particular, above this phase transition threshold, we expect there is no phase transition in the sense that correlations are small. In the sense also we expect of uniqueness of Gibbs measure. So we'd be, we very much want to think about this as meaning that there's just one invariant measure. And indeed, that's what I'm going to prove afterwards. So this is the result, which at this point is not very surprising. What I'm claiming is that there is indeed uniqueness of the invariant measure in infinite volume up until the threshold at which, up until this phase transition threshold. What we can prove, in fact, is that there is a unique invariant measure, first of all. Second, this phi42 field theory in finite volume, there's a unique way of taking the limit, which is, at least to me, wasn't completely obvious. And the two are the same. So the invariant measure is indeed the infinite volume version of the phi42 theory. And we also have a rate of convergence for convergence to the invariant measure, which is given in terms of the so-called log Sobolev constant of the dynamics that I'm going to talk about in a second. Okay, so let me make a few comments on this result before I go into the proof. First of all, I just said we have a rate of convergence, and by this I mean that if you look at the dynamics started from any deterministic initial condition, call it phi0, and look at some nice, smooth, bounded test function f, perhaps Lipschitz as well, smooth, compactly supported, sufficiently nice, then you can quantify the distance to the unique weak limit of your phi4 field theory as decaying exponentially fast up to a sub-leading order correction, which is actually polynomial in time, in terms of this log Sobolev constant. And this log Sobolev constant, some of you may know that it's related to the time it takes to converge from the worst case initial condition. So in some sense, you shouldn't expect to have a better speed of convergence than this log Sobolev constant here for arbitrary initial condition. Now, everything I'm stating in terms of results is valid only for dimension 2. Only talking about phi42, and I'm only talking about phi4. That's at this point, the reason for that is a somewhat technical problem, which I may discuss if I have time afterwards. But what I want to stress, and that I'm going to stress again in the coming slides, is that the method we use, this Holly-Struck-Zegelinsky approach to uniqueness I mentioned at the beginning, is very general in spirit. And so most of our arguments are a priori not specific to phi4. We know how to generalize some of them, but it's just one of them that's giving us some trouble. So that's why we're stuck with dimension 2. So what is this method about? This Holly-Struck-Zegelinsky method is, as I mentioned, something that was introduced in statistical mechanics models, which here I mean as being measures on the discrete torus of side length L. So it's the same as my discretized phi4 theory, except that I only have one parameter, the large scale, the large size regularization, not the small size 1 epsilon. Or if you want, epsilon is equal to 1. And the measures I can discuss can be much more general than what I'm going to write, but let's just look at measures that have a quadratic part, and there's potential here, where the quadratic part, I'm going to think of it as being given by the lattice Laplacian, just the epsilon equal to 1 analog of the regularized Laplacian from before. And the potential, I think of it as being, for instance, some kind of double well potential, so something that's confining, grows sufficiently fast at infinity. Doesn't really matter what it is. The question I want to ask is, what can I say about possible, well, I should say actually more than weak limits of this object, possible Gibbs measures for this object? So I should think of this as having a boundary condition. Sorry, this is a mistake on the slide. So let's say I want to understand let's be very vague. I want to understand what happens to this measure as L goes to infinity. How can I describe this measure in the large size limit? Well, there's many ways to do that, but the idea Holly and Strook had, and then also with Dagallier, was that it was a good idea, if you want to understand the invariant measure, to use the dynamics in order to do so. More precisely, if you understand well enough your dynamics in the sense that if you look at the dynamics in finite volume and control the speed at which it converges uniformly in the volume, so uniformly in L, and uniformly in the initial condition, and also uniformly in the boundary condition, if you have one, then you can use this to construct the dynamics in infinite volume and prove that it's just one invariant measure. So the general idea is use the dynamics to describe the invariant measure. More precisely, the kind of information you get from this approach is what I've started mentioning already. So you can use the general strategy to prove that the infinite volume dynamics exists and is well posed. So you can define the infinite volume semigroup. You can prove uniqueness of the invariant measure and of any possible weak limits of your finite volume measures, and the two are the same then. And you obtain this explicit rate of convergence to the invariant measure. So in other words, their method gives exactly the conclusion I stated in our result for the very simple reason that we're just using their method and adapting it to this singular SPD setting. All right, so how does that work exactly? Well, first of all, I mentioned that the whole idea is to control the speed of convergence of the dynamics uniformly in the volume, uniformly in everything. What's going to be very important is what I mean by speed of convergence. There's different ways to quantify speed of convergence of the dynamics, but the one I want to use is a so-called Log-Sobolev inequality. We say that a measure satisfies a Log-Sobolev inequality if for any sufficiently nice test functions, you have this inequality relating the entropy of the test function under your measure to something that's called the Dirichlet form, just the integral of gradient square, where the gradient here is taken with respect to the field variables. It's not like the discrete Laplacian from before. It's a gradient with respect to the zeta x. Now, this is a functional inequality you should have for the same constant, gamma L. You should have the same gamma L for all your test functions f. Now, why am I saying this has anything to do with the speed at which your dynamics converges? That's because it is a standard fact that having a Log-Sobolev inequality with a certain constant gamma L is equivalent to the entropy of any test function evolved along the semigroup of the dynamics, decaying exponentially fast with a rate given in terms of this gamma L. So you have an exponential decay in entropy of any test function. This particular mode of convergence to the invariant measure of the dynamics is a very strong one, in the sense, for instance, that it implies a Poincaré or spectral gap inequality with the same constant. Completely general. Doesn't rely on the particular form of the mu-L, it's a completely general fact. It also implies exponential convergence in total variation distance through an inequality known as Pinsker's inequality, which just says that the total variation distance is related to the entropy like this. So this Log-Sobolev, having a Log-Sobolev inequality is quite a strong notion of convergence to equilibrium. Now, what is this Holly-Strook-Dagallier method about? It requires three ingredients, and with the three ingredients, it concludes on the uniqueness of invariant measure, the uniqueness of the weak limits of the measure, and on an explicit rate of convergence. The first ingredient is that you want this uniform Log-Sobolev inequality I mentioned. So you want one particular constant such that Log-Sobolev inequality with the same constant holds for your measure on any box of side length L. This is the most important requirement, actually. I'm going to discuss that afterwards. This is the first point. Now, the second point is that what your Log-Sobolev inequality tells you is some kind of decay of, for instance, the law of the dynamics exponentially in time compared to its initial value. But this is only useful if you know that the entropy of the law of your dynamics at time 0 is finite. And it turns out that this is not necessarily the case if you start from your dynamics from a Dirac measure. So if you start from deterministic initial condition, relative entropy of this Dirac measure with respect to the invariant measure is typically going to be infinite. So you need some additional way of knowing that your Log-Sobolev inequality starts being useful after a certain amount of time. So the entropy of the law of your dynamics after a certain amount of time, say time 1, becomes finite. This is the second point that says the entropy at time 1 should be bounded, say, as some polynomial in the side length L. Now, the third ingredient is useful to connect to what we're interested in, which is what happens in infinite volume. The first two objects only have to do with finite volume objects. No, the first two ingredients only deal with finite volume. The third one has to do with locality of the dynamics. You're saying, well, if I want to know what happens to a particular test function supported on a very small portion of space, say a test function that looks like this characteristic function here, where f is compactly supported, then this object should evolve in the same way under the dynamics in finite volume and in an even bigger box in finite volume or even in infinite volume, provided the box is big enough. So this is where it might have been useful to put a picture. But I'm really just saying if you have something that happens inside a small ball and you look at L very large compared to the size of the ball, you don't expect to see much difference between running the true infinite volume dynamics and the finite volume dynamics. And we want this in a little bit of a quantitative way. So qualitatively, you know, it always goes to 0 as L goes to infinity. But we want to know that one can take the side lengths to be polynomial in time. So these are my three ingredients. I want a uniform control, this Log-Sobolev inequality. I want to know that I can use my uniform control starting from any initial condition, so the entropy has to become finite. And I want some kind of compatibility relations saying that running the dynamics in a big box or an infinite volume is more or less the same if I'm just looking at some local quantity. What I claim is that if you have these three ingredients, then you get everything we want. Uniqueness of the invariant measure, uniqueness of the weak limits of the finite volume invariant measures, and this explicit convergence rate. And really, I can rephrase the results. I stated the result we get with Roland and Hendrik in the phi42 case is just saying, well, actually, these assumptions 1, 2, and 3 that I've stated for this statistical mechanics model, UL, if you look at the assumptions, it doesn't really matter that it's UL and not my phi42 field theories that I'm putting here. So if you have the same but for the phi42 dynamics and field theory, then the result is the same. Now, in the remaining time, what I would like to tell you is, well, I'd like to tell you a bit more about what these assumptions mean, how do we check them. But before I do that, I'm going to show you the proof of this claim, if we have these three assumptions. I claim this is just a one-slide proof. It's very simple. If there's any question at this point, I'm happy to take it.
Yeah, so I'm a little bit surprised, not about the claim, but about the fact that you can actually check the conditions, because when Dagallier were doing this stuff, I think that everybody thought that was sort of perturbative theorem. Yeah, that no way that you could get all the way to the critical point doing
Okay, so
the things.
yes, this is an important point. I'm going to come back to that later, I think,
Okay.
depending on what time it is. I may not be coming back to this later. Okay, so what I can say at this point is that there's three ingredients.
We started a little bit late, so you can go a little bit long.
Which means until when?
Let's say you have maybe 15 more minutes or something like that.
Okay. Okay, I'll try to stop before that. Okay, so we have the three ingredients here, and my claim is that they are qualitatively very different. The first one, the Lox-Sobolev inequality, is the only one in which you see the physics of the model. It's the one in which you see the phase transition. If you have it, then you can think about using that method. But usually you only have it at high temperature. So this is, in this sense, indeed their approach is perturbative because having Lox-Sobolev is hard.
Yeah.
It turns out that in the phi4 case, we do have it all the way to the critical point. Also for easing, we have it all the way to the critical point because of some miracle.
Okay.
But in general, indeed, you would only know Lox-Sobolev away from the critical point. In mean-field models, you can also use this. Well, it's less interesting, but it's possible to get Lox-Sobolev all the way to the critical point. Now, the other two, so the second one is just a property of your noise. And having your entropy finite at time 1, you just want to know that you diffuse sufficiently well. It doesn't have anything to do with the physics, just a small distance thing. And actually, that's the one that becomes complicated when you have small distance problems. That's the one we don't know how to do in 3 dimensions. The third item is just a locality property of your dynamics. So this one is true basically without assumptions. Basically without assumptions. Of course, it's more subtle to check in this singular SPD setting, but what I just want to say is that the Holly-Struck-Zegalinsky this Holly-Struck-Zegalinsky business, I put these 3 assumptions on the same footing, but it's more like if you have one, then the other 2 are extremely general and don't really rely on the details of your model.
Okay. Okay, thank you.
And that's what I'm going to try to explain, why it should still be true in this SPD business that the 0.2 and 3 are very general. So let me give you the proof of uniqueness of the invariant measure, one slide proof. I want to characterize invariant measures. To do that, I just need some suitable test functions, and it's enough to look at test functions that are this characteristic function form with a compactly supported F. So I want to prove that this semigroup, there's only really one thing it can converge to in long time. How am I going to do that? The first thing I do is to say that this infinite volume semigroup object applied to my test function, by my finite speed of propagation, it's the same as the finite volume semigroup object on a suitably big box, depending on time, plus an error. So far, so good. Now, I know that in finite volume, I relax to my invariant measure, mu-LT, because of Lox-Sobolev. So I rewrite my semigroup in finite volume as the expectation plus the difference. And the difference I bound using Pinsker inequality and Lox-Sobolev and the entropy finite at time 1. It's small. Third ingredient, I know for some other reasons that I have a subsequence of my finite volume measures, let's call it mu-LTK, that converges just because of some abstract tightness. And this convergence doesn't have anything to do with the test function or the initial condition of my dynamics. This is really just a property of the finite volume measure. So if I take these 3 ingredients together and start back from PTF and run the argument, what I end up saying is that I have a subsequential convergence of my PTF to this object, to the average under this particular weak limit mu. And this doesn't depend on the initial condition. This doesn't depend on the test function. Now, why is that enough to get uniqueness? Well, suppose you have another invariant measure, mu tilde. Just by invariance, you can smuggle in the semigroup. And because we've just shown convergence of this semigroup, we can use dominated convergence, because my f is bounded here, to say that this PTKF converges independently of the initial condition to the expectation under mu. So we have an expectation of a deterministic object, which is just mu. This is true for any test function, so that's it. You see, if we have the three ingredients, the proof is very simple. Now I'm going to spend my remaining time telling you about how we check them and how we check them. So, what I mentioned when Milton asked his last question was that the three assumptions are very different. This log-Sobol F assumption is the one that sees the physics, I said, and in particular, it's very model dependent. If two models have different universality classes, for instance, to use a big word, but different large-scale behavior, then proving log-Sobol F is going to be different. And in general, it's very hard. So either you have it and you can use the method, or you don't, and you shouldn't use the method. But once you have it, I claim that the other two are basically independent of the details of the model. And this is what I'm going to tell you now in a second. So, in the phi4 case, the whole reason why I'm giving this presentation is because we do have the log-Sobol F inequality. I don't want to spend much time on telling you how we proved it. Let's just say there's some renormalization group arguments, abstract renormalization group arguments involved, and a magical correlation inequality. What matters is that we have it until this phase transition threshold, and this is the only place in our argument where we see a restriction, where we see a restriction of the range of parameters we can consider. So that's what I mean also by saying that this log-Sobol F assumption is the only one which is the physics of the model. Now let me just discuss, and I'll only discuss the entropy before stopping. Let me just discuss how to prove that the entropy becomes finite after a finite amount of time. What we want to estimate is the entropy of the law of the dynamics in time t, which I write like this. This entropy of this ft, and ft is just the Radon-Nikodym derivative of the law of the dynamics with respect to the invariant measure. What do people do on the lattice? They do something extremely crude, actually even more crude than what I'm going to write here. What they basically do is they say, well, instead of computing this entropy, which is this complicated ratio of measures I don't know, let's go to measures I do know. So I'm going to compute the relative entropy of the law of the dynamics with respect to the law of the Gaussian measure at the same time. Then the law of the Gaussian measure with respect to the Gaussian invariant measure. This is an explicit Gaussian computation, so I know what that is. And then the law of the Gaussian invariant measure to the full invariant measure. And this is explicit again, because I have the expression of my finite volume invariant measure. So I just do that, which means I reduce the problem of computing my entropy to some explicit Gaussian computations. That are very easy to do with brutal bounds, and the computation of this first term here, which compares the law of the dynamics at time t with the law of the Gaussian at time t, of the Ornstein-Uhlenbeck at time t. This is the difficult part. Now, how do people usually do? They say, well, no, actually, I should say that. This explicit term, to give you an idea of how crude people are being, it's enough to just bound the Laplacian that appears in your measure, this lattice Laplacian. It's enough to bound it by a constant. This is very bad if you think about the phi4 setting, because here you're very much using the fact that you're on a discrete grid, because the Laplacian is in the continuum, as you well know, is not a bounded operator. But the argument people use is just, well, on this lattice setting, it doesn't really matter what the Laplacian looks like, it doesn't really matter that there's these subtle consolations between the field at one side and the field at one other. I could just bound it by the maximum value of the field on each side or something like that. It's a really crude argument. Now, the last remaining bit is the estimate of the law of the dynamics at time t with respect to the relative entropy of this with respect to the Gaussian. The problem you have with this is that you have no idea what the law of the dynamics looks like. But there's a workaround, which is to say this is always bounded above by the law of the Fou process up to time t with respect to the law of the Fou Ornstein-Uhlenbeck up to time t. This is a priori a much bigger object, but now you have an explicit expression for this by Girsanov. And this explicit expression, again using very crude bounds, is enough to give you the bound that you see at the top.
Sorry, Benoit.
Yep.
In this last bound, like bounding the entropy at time t by the entropy of the whole process,
yes.
Can you give me a sense of what you lose by doing this crude? I mean, maybe it's not crude actually, but what do you lose when you do this upper bound?
It's a bit difficult to. Okay, so what I can tell you, but I don't know how good of a picture it's going to be for you, is what happens precisely in the phi42 setting.
Yeah.
Which is my next slide.
Okay.
Where what happens is that is this point item 2 here. In dimension 2, the law of the phi42 dynamics at each time is absolutely continuous with respect to the law of the Ornstein-Uhlenbeck at a given time. So at fixed time, you have absolute continuity, which means the entropy has a chance of being finite. However, if you look at the law of the Fou process up to time t, then you lose absolute continuity. And one way to see it, it's actually very easy to understand why, if you have time to write down the computation. If you think of this, these counter terms I mentioned at the beginning, these are very subtle. So the counter term was precisely designed so that the phi to the 4 term, for instance, has a limit, phi to the 4 plus counter term phi square. If you square phi to the 4 plus counter term phi square, you don't have a limit anymore. It blows up as epsilon goes to 0. This is precisely what happens in Girsanov, because the Girsanov term is like Laplacian of the drift in USPDE minus gradient square of the drift in USPDE. And this gradient square means everything blows up. It's not so easy to see if you haven't done the computation, but yeah, it's really related to the small distance irregularities of the field in this particular instance.
Okay, thanks.
And I guess another way to see it, which is, I guess, yeah, one way you may be more accustomed to is if you think of hydrodynamic limits, say, if you think of a symmetric interacting particle system, so you want to look at it in diffusive timescale, perhaps, which means in your Hadron-Nikodym derivative, if you compare, I don't know, with a drift and without a drift, you're going to get a huge exponential, so an exponential of an integral in time. But this time is huge because you're accelerating of order n square in time. So if you do things a bit wrongly, this exponential of the integral in time over a very big time interval may be considerably bigger than order 1, which should be the right size of your relative entropy at fixed time.
Yeah.
I don't know how clear that was, but you have an integral in time, and if your time interval is big, that's when you might lose compared to computing things at fixed time.
Yeah.
That makes sense?
Yeah, in a particle system setting, the point would be that you have to consider a drift that is of the right order to produce a trajectory that would be doable in, for example, in a large deviation setting or something.
Something like that. But I guess if your drift is just too big, at fixed time, you may still have something reasonable in terms of invariant measure.
Yeah, of course. Yeah,
even though you get an exponential in time for the law of the Fou dynamics up to this point.
Yeah, okay, thanks.
Okay, so I guess I should really stop here. So let me say just one last thing, which is what happens in this phi42 setting. there's one first problem that I mentioned, that we can't use the simple trick of bounding the law at time t by the law of the full process up to time t. However, it's not a big deal. It's not a big deal because you can be a bit more clever and do essentially the same thing, in the sense that you're only interested in having the right law at time t. You're not interested in how you get there. And it turns out there's a general strategy, so-called time-changed Gesanoff method, due to Mattingly in Sweden first, but then used quite a lot by Mattingly and Heyer. And well, Jonathan Mattingly, I guess, is the expert, which gives you a general procedure on how to arrive with the right law at a given time, but not necessarily following the Langevin dynamics, but something a bit better. And in particular, it's possible to arrive at the same law just by a simple change of your time variable. It's just a change of time variable, really. The same law, but for an SPD which has a smooth drift, a drift regularized by a convolution with a heat kernel, something like this. Okay, so this is much too fast, and I don't have time to explain this properly, but let me just, the point I just want to make is that this relative entropy computation is much more delicate in the phi42 setting because of all these divergences at small distances. In particular, a naive Gesanoff argument breaks down, but still there is a general prescription on how you can repair this Gesanoff argument. And in particular, this the way you repair this does not have anything to do with phi4. It works for very general interaction. For this part of the argument, you can hope to extend, even though for now, things are restricted to dimension 2. And I won't have time to discuss the finite speed of propagation, so perhaps it's best I stop here, and thank you for your attention.
Okay, thanks very much, Benoit. Are there any more questions?
Okay, so I still have some questions. First, I would like to thank Benoit for this very interesting talk. It's
Thanks.
Also very clear and very well explained. So I don't know if this is related to that. When you do homogenization, sometimes, and you want to do this Yersanoff method,
Yep.
if there is this sort of epsilon expansion that people do, and if you take instead of comparing with the Langevin dynamics, you compare with some further terms in this epsilon expansion, you get better Yersanoff.
I'm not quite sure I see what you mean. So the epsilon expansion, you mean in dimension 4 minus epsilon, for instance?
No. What I meant is that so usually so you know in homogenization, what you do is that you solve the cell problem, and then that gives you should be the limiting diffusion.
Yeah.
And then you can compare. If you do Yersanoff of your original diffusion with respect to the homogenized one, you get a drift which is too big. Then what you do is that you go to the next expansion in this cell problem, and you get some epsilon corrected diffusion. And if you do Yersanoff with respect to that one, you get a better drift. And sometimes this works, sometimes it doesn't work, but I mean, it's a way to make things better.
I'm not sure it's completely the same. The way I understand this Mattingly method, actually using his words, is somehow you have a fixed amount of noise you want to add to your dynamics to get up to time t. But there's a lot of ways, there's a lot of different drifts that take you to the same place, in a sense. It's just deciding, you're just deciding on the path, which I think is a bit different
Yeah, it sounds different actually. Yeah.
I don't know. I must say this. I have never worked with this homogenization. I don't know exactly what you're talking about, but yeah,
Okay.
just feels to me superficially that this the philosophy might be a bit different.
Okay. Okay. Well, thank you.
Are there any other questions? Okay, so if not, let us thank Benoit again for a very clear talk. And
Thank you.
Milton, I don't know what the rest of the schedule is for the month, but is there a talk next week?
Yes. So I think it's so Hubert sent me an email about it. So I think it's maybe Charbord and Ave or I have
Okay.
to check, but I think it's
Okay.
but there
You'll
is
send the announcement, right?
but there is there will be certainly a talk next week.
Okay. Thank you again, Benoit.
Thanks.
Bye-bye.
I guess, yeah, have a nice day, probably.